This is about digital signatures. How do you sign a document digitally? And now it is legally binding nowadays. And all of you can sign a document that the bank will accept. Some banks will accept, let me put it this way. And so we are going to talk about as to how to do that. So first of all, what is the basic theory behind digital signatures, and then three different methods: ElGamal, Schnorr, and DSS. So this is the standard which is based upon these two. So there's a lot of repetition because this is based upon that, and that, this is based upon those. So I mean, like, it's just the same thing repeated 3 times. So digital signature means that we should be able to verify the author, date, and time of the signature, and we should basically authenticate the message content. So I mean, basically the message content that you signed, you cannot say, well, I didn't sign this one, I signed that one. You changed it. So obviously integrity is part of it. So this is somewhat related to the MAC issue, but here really what we are suspecting is the person who sent the message, not the attacker. We want to make sure that the person who sent the message doesn't say something different later on, that I didn't say that I owe you so much money. Right? So the sender is a potential threat. So here the sender is Bob. Bob has a message. It digitally signs that message. So that signature is here. That signature is sent to Alice. Then the Alice can do several things. First of all, she can verify that the signature is correct, and she can go to the court, and the court can verify that the signature is correct, that the message has not been modified by Alice or anybody else. So one simple way would be like we did for the Mac, is that you create a hash and you encrypt that hash with the private key, and then you can compare with the public key, and that is simplest way. The kind of attacks that one could think about, now here I'm not talking about the attacker being the source, but other people could change. And so A is the victim and C is the attacker. So key only attack. So if C knows only A is public key, what can he do? And everybody knows A is public key. Right? Can you do some things? So we want to make sure that, those attacks are very difficult to attack, in the first place, but we want to make sure that our algorithm is such that somebody knowing the public key cannot change things around. Known message attack. Now C could collect a list of documents that you have signed. So you sign your annual contract every year with the company. Now you have 10 years contract, we have 10 messages and 10 signatures. We could do something with that. Right? So a set of messages and signatures, from based upon that, what kind of things we can do. Our generic chosen message attack is that C obtains A's signature on a message selected without the knowledge of A's public key. So C doesn't know A's public key, but C gives a message to A, says please sign it. A signs it, and then now the message is such that somehow C can figure out something from that particular message structure, what A's credentials are. Our direct chosen message attack, where C obtains A's signature and knows A's public key. So first he knows the A's public key. Based upon that, he designs a message. And then adaptive chosen message attack, C may request signatures or messages depending upon the previous message signature pair. So you do it like this. You give them a message and get the signature. Then you study it a little bit more. Then you say, okay, now if I get this one more, I will know more. So you send another message which is especially formulated. And then you get 2. Now you do something more, and then you get 3. And so these are all designed based upon the previous signatures and messages. You generate new messages. So somebody actually wrote a paper in which they wrote down these are all possible attacks. Now when I read this list, I am not really sure whether this is a really good list, or this is a comprehensive list, or this is the only list. But since nobody else has written a paper since then, so the book is talking about this paper, which is kind of old. We'll just stick with the list that these are possible attacks, but there could be more attacks as far as I'm concerned. I haven't done myself the analysis. So as a result of this attack, what can happen? First of all, somehow C can come to know A's private key. That means the total breakdown. Now you are no good. Your identity has been stolen. Now C can act like A. Second thing is, C doesn't know the private key, but C can generate signatures on any message. Somehow C can generate the signature. And I don't know how they will do it, but again, this is the same paper which talked about the attack, talks about these forgeries. So they say one possibility is that you don't know the key, but you can still generate the signatures. Okay. Selective forgery. You cannot generate signature on any message, but you can generate signature for a particular message. Which C designs. C says, well, I cannot generate for all these, but I can generate for this one. Or it can generate for a message not chosen by C, and C can generate. You give him a message and he says, okay, here's the signature, without knowing the key. So these are all possible scenarios, and again, I'm not sure whether this is the complete list or or not complete list. But this is that paper that is quoted in the book. They talk about so many attacks and so many forgeries possible. So we just make the list. So if you want to have a signature, first of all, the signature must depend upon the message signed, must use the information unique to the sender. So it should be something that if I sign and you sign, the signature should be different. And if I sign message 1 and message 2, the signature should be different. So use sender to prevent forgery and denial. So that way, if it is unique to the sender, then nobody can forge it and nobody can deny it. Must be relatively easy to produce and relatively easy to recognize and verify. I should be able to sign fast and you should be able to verify fast. We do sign, if you have not done the closing of a house. If you do closing of a house, on the closing day, we sign about 100 pieces of paper in 1 hour. So you don't even read the whole piece of paper. You say, okay, give me the next paper, sign, sign, sign. So same thing, if it has to be done digitally, we have to do it very fast. And directed signature means recipient can verify. So directed signature is signature which is specially designed for one person. So you can verify it because we have some shared secret. On the other hand, we could have an arbitrated signature, which means that anybody can verify. You can go to the court. Arbitration means going to the court, or going to a judge, or going to somebody who is the middleman, right? So anybody can verify that is arbitrated signature, and that's what we are going to talk about most of this lecture. We are not talking about directed signatures. We are talking about arbitrated signatures. Should be computationally infeasible to forge. So while it is easy to produce, but difficult to go the other way around. So with new messages for existing digital signature, you should not be able to get new messages. So this, we have repeated this for the hash, we have repeated this for max, and we are going to do the same thing for signatures. They're all one-way functions, and they're all related. With fraudulent digital signature for a given message, and we cannot create signatures, be able to retain a copy of this signature in storage. And second thing is, we should be able to store it. So it's not like signature, you signed it and then disappears. So we should be able to store it, and 10 years from now we should be able to say that this is what we signed 10 years ago. The first method of signature that is generally presented in the books today is ElGamal's, and this is actually very similar to the encryption method that he has, which is very similar to DH, Diffie-Hellman, and they all the three signature methods actually are related to this, and therefore they all use similar things. The exponentiation in a finite Galois field. So they will use exponentiation, and they are based on difficulty of computing discrete log, just like in the encryption. So what you need is, you need a large prime Q and primitive root A. So everybody understands what is a primitive root? What is a primitive root for Q? What does it do? Anybody? What is the property of primitive root?
Powers that generate this field.
Whole thing. So the Q alpha Galois field of Q will have numbers from 0 through Q minus 1, and if there is a number which can generate all of them, that would be the primitive root. And there are many primitive roots of Q, but basically alpha raised to square, alpha raised to 3, you keep doing that, alpha raised to Q minus 1, and you will get all of them. So you need a primitive root of Q, and then you select a private key XA. Obviously the private key has to be in this field, so it is between 1 and Q minus 1. 1 is not a good number and Q minus 1 is not a good number, therefore these things are strict. And then you compute your public key by taking exponentiation. So YA is your public key, XA is a private key, and nobody will know XA. They might know YA but cannot compute XA. That's the whole difficulty. Now, before I go into this method, one thing that we do in encryption, and I think I said this in the beginning, is that we don't use the same key n times. We don't use the same key many times, right? So if you're going to sign, you're going to sign hundreds of documents in a day. So you're not going to use your private key every time. If you sign hundreds of documents in a day, somebody can sit down with those documents and tell your private key right away, right? So what you do is, in these methods of signature, first thing is that you generate a random number and you sign that document, and then you generate another random number for another document. So every document signature is generated using a different random number. Okay? So if people have 100 documents, they cannot, really correlate with, because each one of them is different random number, right? And so that's the key. So you need to get what we call a message key. Message key is a key that is used for this message only. You don't use it again for another message. All right? So to sign a message, you hash it, and now you generate a integer k, which is a random number. You select, actually choose a random number k, which is your message key. It has to be such that it is relatively prime to Q minus 1. Okay? Relatively prime to Q minus 1, and then that is your message key. Then you generate, so this is your secret, now you generate a public number from that. So you get S1 is equal to A raised to K mod Q. Right? So this is a public number S1. In fact, S1 is what we are going to send as part of the signature. And all that is that random number K that we generated, A raised to K mod Q. Now you have to calculate K inverse mod Q minus 1, and then multiply that to M minus XA S1. So you did use your private key, you did use your private key XA here to multiply and subtract it from M, and then multiply by this K inverse, and this is what is called S2. So this is your signature. S1, S2 is your signature. So the main difficulty here is that if you cannot invert S1, because if you could invert S1, then you could figure out what K is. Once you could figure out K, you could figure out K inverse, and you could do a lot of other stuff. So the main thing is you cannot take the log, and therefore you cannot find out K. And if you want to verify the signature, then the way to verify the signature is that you calculate V1, which is A raised to M mod Q, where M is the hash. Little m is the hash. Little m is the hash of the message. You take A raised to M mod Q, and you calculate V2 is equal to YA, which is your public key, raised to S1, and S1 raised to S2 mod Q. Now there is a slight confusion, and I just want to make sure you understood that there are two mods here. Sometimes we say mod q, sometimes we say mod q minus 1. Okay, so you have to be careful which line you are on. So here we are mod q. If V1 is equal to V2, then the signature is valid. So why V1 equal to V2 signature is valid? Because V2 is this complicated expression ya raised to S1. If you write down ya is a raised to xa raised to S1, and then times S1 raised to S2. S1 is a raised to k raised to S2. Both of these are power of a's, so this is a raised to xa times S1 plus k times S2. Now k times S2 is simply the quantity here, m minus xa S1. So that is m minus xa S1 plus xa times S1, you put there, and these cancel out, so this is equal to a raised to m, which is V1. So V2 equal to V1. So after all this mathematical multiplication, you figure out that if you did all this, then V1 will be equal to V2. Yeah. But anyway, I don't know whether you can keep all of this straight in your head, but one thing to remember is that we generate a random number k, which is your message key, and somehow we generate the first secret using that key so that the key can be transported. So you are sending the key by sending S1. This is in some sense similar to Diffie-Hellman. In Diffie-Hellman, you generate a random number as your private key, and then you g raised to that, you send it to the other side, and the other side raises it to that power, and then they figured out a common secret. Exactly similar thing is being done here. You're sending S1, and then the other side can raise things to S1 and then somehow calculate some things. So that is what is happening here. K is the secret that is being sent in the form of S1, and then S2 is being calculated, so that if you knew K, you can easily basically verify all that. And you really don't need to find out K in this process, by the way. To verify, you can do verification simply by calculating these S1 and S2 stuff, which you know. Alright, so here is an example. 19 is our large prime number, and A is 10. So when we are talking about the Galois field, we had a table where we had the whole table for 19, and we made a list of all the primitive roots, and for 10 turned out to be a primitive root, because all powers of 10 will generate the 18 numbers or 19 numbers that we need. 18 numbers that we need, not the 0. It will generate all the 18 numbers that we need. So A chooses xa is equal to 16 randomly and computes 4. Right, so that is the public key. Then A signs the message m is equal to 14. So this is the message, and instead of giving the message, they are just giving the hash 14 as 3, 4. How did it get 3, 4? First, it chooses a random k equal to 5, because it is co-prime to 18. Common factor is 1, and therefore if you use 5, then all you do is S1 is equal to 10 raised to 5 mod 19, which is 3, and then you find k inverse, which is 5 inverse mod 18. Now again you have to remember how to find the inverse. For these small numbers you can do by inspection, but generally you need what? How do you find the inverse? Table, yeah, that table we talked about. So you can find that, you will find 11. So then you can compute S2 by k inverse times m minus s times S1 times, where is S1? 3 times XA. XA was 16. So you send, so S2 is 4, S1 is 3, and you send 3, 4 as the signature. Then to verify, you take calculate V1, which is 10 raised to 14 times mod 19, 10 raised to m is 14, 16, and V2 is, V2 was YA raised to S1 times S1 raised to S2. So YA is 4 raised to S1 is 3 times S1 is 3 raised to S2, which is 4, and you get 16. Now before I go too much into signatures, does anybody know how do you, has anybody signed any documents or has seen any signatures on any document? Have you seen?
Well, then you could have argued the SSG that was signed.
That was signed, but so that is certificate. But there is another way, another thing I want to let you know, that if you use Acrobat, Adobe Acrobat, it lets you digitally sign the messages. So you could, for example, I received a message from another company I was signing a contract with, a digitally signed message. So basically, it was a PDF, and you have to pay, I think, to Adobe to get some secret thing like that, whatever it is, to get this certificate or something like that. Once you get that certificate installed in your Acrobat, you can start signing, and that is accepted in the court of law. Okay? So it is here right now, in the sense that in everyday use, lawyers use it all the time to sign documents. Although I am kind of little bit leery of Acrobat, because in Acrobat, when I get anything encrypted, so my bank sends me statements, encrypted statements in the mail, right? It's trivial to break that encryption. So I have a program which simply breaks PDF encryption. So given that program, I find it, I don't know how strong their signature thing is, but encryption is very weak. All right. So moving on to Schnorr's. Now Schnorr's is very similar to ElGamal's, and slight differences. Basically, the slight difference is that the message dependent computation can be done in the idle time. So Schnorr actually came much later. Actually, it might have come about 10 years after ElGamal. Obviously, it has to have something new, and that new thing is that you could calculate everything in idle time, and then when you have to sign, you can do it fast. So you do the same thing now. If the book keeps changing the numbers, so now they are using a prime modulus p, and p minus 1 is the number of which you take a factor q, which is a prime factor q. So q is a prime number, and generally we use q of 160 bit and p of 1024 bits. And the reason q is 160 bit is because we are going to use SHA hash. And so then once you have selected P and Q, and obviously P and Q, by the time you select P and Q, it will be years. So what they have done is P and Q is a fixed number that you can look up in a table. In fact, I think they are listed in some RFC. Okay. It's time about. Okay, I'm sorry. So let's stop right here.